This lesson deals with the analysis of circuits with dependent sources. You can find these notes in the ECE201 ebook in Chapter 4 starting on page 3. The circuit reduction techniques that we learned earlier in the course can be applied to our active circuits, but you got to be careful that you don't eliminate the controlling variable. For example, if you had the voltage across a resistance and that was used to control a voltage or a current, and you source transform that resistance, although the resistance stays the same, the voltage across it usually isn't. For Thevenin's and Norton's theorem and superposition, we're still going to use that theorem, but we're only going to set, again, the independent sources equal to 0, not the dependent. You can source transform, though, the dependent source, and sometimes it's very useful in solving problems. We'll look at some examples of this in the chapter. We can also do the mesh and node analysis by inspection if we do a slight modification to handle the dependent sources. Again, we'll look at that a little bit later in the chapter. Let's just do an example of a circuit that has controlled sources in it, and let's see if we can analyze it. This example is from ECE201 and is dealing with an equivalent circuit of what's called a common-emitter amplifier. So given this circuit, which has a voltage source, some resistances, and then one dependent source where this current depends on this current, can we solve for some of the things in this circuit? Well, in electronics, the things we're interested in are what's the voltage gain, so the voltage from the output to where we can measure the input. This is usually a sensor or a microphone. We're also interested in what the input resistance is, looking into our circuit. This will determine really a voltage divider with our source, and so we want to keep the input resistance as high as possible if we can. And lastly, another thing that's of interest to us is the ratio of output current to input current. Transistors are basically amplifiers of current, and so we're going to look at voltage gain and current gain. So let's even solve for these three ratios. And I don't put a value for V sub s here because it's a linear circuit, and these controlled sources are also linear. So let's solve for V out. Now the current in these two resistances in parallel would produce the output voltage. So that's going to be the current in this direction, and that's going to be a minus 100 I sub B with 1K in parallel with 2K. After you multiply that out is about minus 66,700 times I sub B. So I have the output in terms of I sub B. What is I sub B in terms of my input voltage? Well, just Ohm's law here. I've got the voltage across our pi here, the same as the voltage back here, and so the current I sub B is just Vn divided by R pi, which is 631 ohms. So if I substitute that back into my last equation, I can solve for the output over the input. And all this is right down below here. Here's my V out in terms of I sub B, multiplying all that out, and then substituting I sub B as Vn over 631. Put that over here. I'm getting a minus 105.7 times Vn. So I have a voltage gain of a minus 105.7. We give this a special symbol, capital A sub V in ECE201. Now there's a minus sign here, and what this means is that if you put a sine wave input, the output is going to be phase shifted by 180 degrees. In other words, when the input goes up, the output goes down. This is actually useful in some applications for boosting signal across a load. Let's find the input resistance to our circuit. That's simply the ratio of Vn to In. But all I've got here are three resistors in parallel. So whatever this voltage is, the current that's going to flow is by Ohm's law. These three in parallel turn out to be 531 ohms. So the ratio then of input voltage to input current is just that 531 ohms. We call that the input resistance. Again, why this is important is that this forms a voltage divider with V sub s. What that's going to do is cut the signal down before I amplify it. I'm going to pick amplifiers where the input resistance is much, much higher than the source resistance. And we'll look at that in ECE201 and picking amplifiers and composite amplifiers. The last thing is to solve for the current gain. But I actually have some of that information already. I out is just V out divided by R sub L, and I in is V in divided by R in. Take the ratio of those two, we have the current gain. The output voltage we just showed was a minus 105.7 times V in, and so in taking the ratio of these two, the V in drops out. 531 comes up in the numerator, and then we multiply these two and divide by 2K, and it turns out to be a minus 28.1. This is called the current gain, and usually given the symbol A sub I. And you can see here that the current gain depends on the voltage gain, actually times Rn divided by R sub L. We also calculate a thing called power gain for amplifiers, which is the product of the voltage gain times the current gain. And since the current gain has the voltage gain in it, we'll always get the same sign for both of those. And if they're both negative or both positive, the result will always be positive. And what this means is that the output resistor is getting almost 3,000 times more power than the resistance Rin is getting. Now, where's all that coming from? Well, the controlled sources are created by using power supplies or batteries. We don't show them in the equivalent circuit here, but we'll learn about this in other courses. There is no free gain here. We're just simply taking the power from a battery, which is a DC source, and pulling current out of it in an AC fashion, using that to create an overall power gain. But when you add up all the power, it does sum to zero. So whatever is generated, you can find where it's absorbed. We'll do examples like this in ECE201msu, just showing that at every instant in time, the power in equals the power out. Let's do another example with controlled sources in it. This is also taken from ECE201 and is called an emitter follower. This is the equivalent circuit of a transistor, actually biased in what's called the active region. So here again, I've got a bunch of resistors, one controlled source, and that's controlled by the current in this resistor R pi. Once again, let's find the voltage gain, input resistance, the current gain, and then the power gain. So the output voltage here again would be these two resistors in parallel, and the current that's coming in here is equal to 200 IB plus I sub B. So I got 201 I sub B coming in here, and then times the resistance. 2K in parallel with 1K again is 667 ohms, and then multiplying that by this would give me the voltage out in terms of, again, I sub B. So I need another equation relating V in, V out, and I sub B. I actually have one right here. This is V in, so the rise in voltage would equal the drops around the loop. So V in is equal to IB times 1.26K plus V out. This is shown on the next page. So here's our first equation with V out in terms of I sub B. The second equation with V in terms of I sub B and V out. Now let's substitute in from the first equation this 201 IB times 667. I'll take common I sub B here, and I've got I sub B times 1.26K plus 201 times 667. I can go back and substitute that in back over here. So V out is 201 times 667 times I sub B, but I sub B is V in divided by this. Turns out the answer here is 0.991. For this particular amplifier, the voltage gain is actually never greater than 1. It's always less than or equal to 1. In terms of an amplifier, I'm not getting any voltage increase, but hopefully I'll get a current increase. The reason this turns out this way is that the term here in the denominator is also in the numerator, and there's also a term added, which is that resistor labeled R pi. So this is one of the disadvantages of this amplifier. I can't get a voltage gain out of it. The circuit is sometimes called a voltage follower in that the output follows the input. Let's find the input resistance of this circuit. Go back to the previous page. Let's erase this right now. But the resistance looking in here again is the ratio of this voltage to this current. Well, I've got R1 in parallel with R2, and then I've got this thing here. Think of this as a box, and the ratio of this voltage to this current would be the resistance looking in here. Voltage cross here is V in, and the current is I sub B. But we actually derived an equation for that as part of our gain amplification calculation. So let's use that to then find the parallel combination. So 100K in parallel with 100K in parallel with the ratio of V in to I sub B. That's on the next page. V in terms of I sub B. So I have 100K in parallel with 100K, and then I've got 1.26K plus 201 times 667. That's about 135K, and the parallel combination here would be 50, so we're a little smaller than 50, so 36.5K. What's interesting here is the controlled source in our problem has taken this 1K and 2K in parallel, making it look like it's 201 times bigger. A controlled source is not a resistance, it's simply a relationship between voltage and current. Now let's calculate the current gain. Again, I got the same relationships here. The current I out is V out over R sub L, but V out is the voltage gain times V in. The current coming in is V in over R in, and that's going to be V in over the 36.5K. So again, the ratio here, the V ins drop out. The current gain is equal to the voltage gain times the input resistance divided by the load resistance. And that turns out to be 36.2. It's a handy formula to remember for a quick calculation, but again, you can just go back and just do Ohm's law. Let's see what the power gain for this is. So we got no voltage gain, but we've got a current gain, and the overall power gain is about 35.8. And these are some examples of circuits that have controlled sources.